This is the second in a two-part video about calorimetry. In the last video, we defined the conservation of energy and how Q equals MCAT. And in this video, we'll do some calculation examples using that concept. So we'll start with a simple calorimeter example. This is the same picture that I drew in the last video. I'm just going to add some numbers to it. So let's say that that piece of metal that I tossed into the water, let's say that that was a 150-gram piece of lead, and that I had heated it in boiling water to make it really hot before I dropped it in, and it was around 100 degrees Celsius. And let's say in this box that I filled it with 50 grams of water, and the 50 grams of water was at 22 degrees Celsius initially before anything happened. And after I added the metal to the water and I waited for the temperature to equilibrate, the final temperature for everything was 28.8 degrees Celsius. Let's try and solve for the CSP, the specific heat of lead. So the first thing we need to do is we need to turn all of this information in the word problem in the picture into an equation. So we need to find each of the Q pieces in our scenario. So one of the Q pieces is going to be the heat of the metal. And the other Q piece is going to be the water. So the metal and the water make up the entire setup, and the sum of their heats should equal 0. And we can use a Q equals MC delta T piece for each of those Qs. So we'll have M of the metal, CSP of the metal, and temperature change of the metal, plus mass of the water, CSP of the water, and delta T of the water. And the sum of those should equal 0. So let's check out which variables we know based on our info from the problem. So the metal, we know the mass of that. Check. The specific heat capacity of the metal, we are trying to find that in the problem. The temperature, remember delta T is TF minus T initial. And we do know both the initial temperature for the metal and the final, because the final temperature is the same for everything. Mass of the water, we know. Final minus initial temperature for water, we know, 22 and 28. And then for the specific heat of water, this is going to be your new favorite number for this chapter. For water in the liquid phase, the value is 4.184 joules per gram per degree Celsius. Almost every calorimeter setup involves water, so you will be using this number quite a lot in this chapter. Okay, so it looks like we have all the numbers we need, and we're ready to set up the calculation. All right, so the mass of the metal is 150 grams. We're trying to find CSP of our metal, of our lead. Final minus initial, make sure you're careful and you grab the right ones here. So the final temperature of everything was 28.8 degrees Celsius. And the initial temperature of the metal was 100. Remember, this is the only time in this entire chemistry course you will be allowed to use Celsius, so enjoy it while it lasts. Mass of the water, 50 grams. CSP of the water, 4.184 joules per gram per degree Celsius. Oops, I've run out of room. Times final temperature is the same for everything. Minus initial temperature of the water, that one was 22. And that equals 0. Or use of space there. You know what I mean. And if we double check, the metal should be going from a hot temperature to a cold temperature. The water should be going from a cold temperature to a hot temperature. So make sure that that works. All right, math happens here. Little rearranging, little calculator. We should end up with positive 0.133 joules per gram per degree Celsius for lead. And if you look that up in a reference table, or if you Google it, you should find that that's pretty close to the standard value. And one note, while we're here, while we're calculating these values, these specific heat or heat capacity, those numbers will always be greater than 0. These are always positive numbers. So if you solve and you end up with a negative heat capacity, you probably want to go back and try that again. Okay, so this is an example of how to do a calorimetry problem. And this type of setup, like the very simplified version that I drew up there with the cube in a box of water, this is called a calorimeter. Calorimeter measures heat flow. And that can be of a physical process, like the one we just did, where one hot thing warms another thing, or it could be a chemical process, where an actual reaction happens that absorbs or releases heat. Calorimeter. And the reason it's called a calorimeter is because there's another unit of energy that we use in America called the calorie. And that's another way of measuring how much energy something has. Specifically, food is what we use it for. So 1 calorie is equal to 4.184 joules. If you're talking about calories on a cereal box are kilocalories with a big C. And those are 1,000 times bigger. So that's 4,184 joules in a kilocalorie. Okay, so most calorimeters are a little bit more advanced, but not actually that much more advanced than this picture that I drew. So there's 2 main types of them. The calorimeters can either be at constant pressure or at constant volume. And I'm going to show you some example pictures taken out of the book for these because they're a little bit more complicated to draw. So the constant pressure calorimeter, this one is called a coffee cup calorimeter because we often make it out of styrofoam cups, 2 of them, of course, when we're in the laboratory. So here's a picture of a coffee cup calorimeter. This came from page 474 from your textbook. So if you want to quickly find that page or draw this picture, you can pause the video here to do so. So in the coffee cup calorimeter, we can confirm that this is an isolated system. So this is closed. There's 2 styrofoam cups for the bottom and some sort of a lid for the top. So no mass and no energy can escape from this setup. There are a couple of holes in the top, one for the thermometer so we can measure the temperature, and one for a stir rod so we can keep that solution mixed around and evenly distributed inside, even with the lid on. So you're really missing out on making lots and lots of noise stirring these silly coffee cup calorimeter contraptions. Okay, so that's our coffee cup calorimeter, and it's kept at constant pressure. So if there's an increase or decrease in the number of gas molecules on the inside and the pressure in the system changes a little bit, the walls of the coffee cups can flex a little bit and adjust for that change in pressure. The other type of calorimeter is called constant volume, and these are lovingly called bomb calorimeters due to the explosive nature of the reactions they are traditionally used to measure. So here's another picture taken out of your book. This one's page 482, if you want to look it up yourself. And bomb calorimeters tend to be a little bit pricier than 2 styrofoam cups and a lid. You need to have a fancier instrument with metal walls that don't expand and don't change volume when a small explosion occurs. So there is a small sample cup on the inside that's wired up and filled with high pressure oxygen plus whatever compound it is you're trying to burn. When you ignite it, the compound is exploded and it causes heat, and the heat is transferred out into the bigger compartment, which is filled with water. And that water absorbs the heat, and then a computer uses a thermometer to measure how much energy was transferred. So in this case, even if the number of moles of gas increases or decreases here, the volume of the system doesn't change. I've never actually had the chance to use a bomb calorimeter, but I have used something similar to do a reaction, and it can be really helpful to keep constant volume because you can change the pressure inside of your container without fear of it exploding and making a mess all over the place. So now we've talked about calorimeter types, we've done a simple example. Let's do an example that's a little bit more difficult for a reaction, a chemical process this time. So here's a chemical reaction. So let's do an acid-base reaction that mixes a strong acid, hydrochloric acid, with a strong base, sodium hydroxide. This is like a preview of topics to come later in the course. So let's say there's 25 milliliters of 2.5 molar acid and 25 milliliters of 2.5 molar base. So same volume, same concentration are mixed together. And as we know, acid-base reactions create heat. They're exothermic. So both of those solutions were at 21.1 degrees Celsius initially, and the temperature rose to 37.8 degrees finally, and they were mixed in a styrofoam calorimeter. And we need to find the heat of reaction. So the styrofoam calorimeter, that's our constant pressure setup. And to find heat of reaction, we need to think of what the pieces are in the reaction. So this one looks a little bit different than the last example where there was a piece of metal and a piece of water. On first glance, it looks like there's only one piece. There's just this stuff that was added. The calorimeter was initially empty. But here's your clue in the question, heat of reaction. So we're going to say that the HCl and the sodium hydroxide, those are the pieces that are reacting. And that is one piece. And these solutions are aqueous. And aqueous means that some of the solution is HCl and most of it is water. So that means that the water, the solution, is the other piece in the equation. So there is the HCl and the sodium hydroxide piece, and there's the water piece, the solution that they're dissolved in. So let's rearrange that since there's just two pieces. Since we're solving for Q of reaction, we'll isolate that. That's equal to negative Q of the solution of water. Okay, so we know that each Q piece is an MCAT, so negative mass of the solution. The CSP of the solution, and the change in temperature of the solution. So there's a few assumptions that we're making here. So when we're calculating the mass of the solution, the mass of the solution is the hydrochloric acid and the sodium hydroxide mass added together. Because aqueous solutions are mostly water. So we're making that assumption here, and we didn't get the mass. Notice we got the volume and the concentration, so we are going to need the density to convert to mass. The density of water is 1 gram per milliliter. So that should be enough information to get us rolling. So let's have a go here. Q of reaction equals negative mass of water. So there were 25 mils of this one and 25 mils of this one. So that's 50 milliliters in total. And we'll assume both of those solutions were mostly water. So we can use the density of water to convert from volume into mass. So 1 gram per 1 mil will give us mass. We'll use our new favorite number, the specific heat of liquid water, 4.184. And the final temperature was 37.8. The initial temperature was 21.1. All right, milliliters cancel, grams cancel, Celsius cancels. We should end up with joules. And then quickly before we solve, I'm going to make a prediction about the sign. So since I know that acid-base reactions are usually exothermic, and I observed the temperature increased, it looks like the heat is moving from the system into the surroundings. And if you remember, we define this type of a reaction as exothermic. From system to surroundings. An exothermic reaction, the Q value is negative. So I'm looking to see the Q of reaction is going to be a negative number when I finish the problem. All right, so we plug that into the old calculator, and we end up with a negative 3493 joules. This is a kind of a big number. We can quickly convert to kilojoules to make it look a little nicer. Negative 3.5 kilojoules. And as I predicted, Q of reaction is a negative number, meaning this is an exothermic reaction. So there are different types of calorimetry problems that you'll see. Sometimes you solve for temperature, sometimes you solve for mass, sometimes you solve for specific heat, and sometimes you solve for an entire Q piece. But you should be able to rearrange these and add in 2 or more Q pieces to your equation to be able to solve for the different parts of the heat of reaction to measure the calorimetry. In the next video, we will talk about how we can measure heat as an extensive property as enthalpy.